Continuing in the force lecture series, I'd like to look at how to solve horizontal multi-force problems. We'll deal with vertical multi-force in a separate video. So for this one, I just want to concentrate on forces acting in either positive or negative directions on the x-axis. The only equation we're using is Newton's second law in this version. And just keep in mind now that the net force now really does mean you want to add up all the force vectors acting on the object. There are very few equations you need to solve force problems, but the key one is Newton's second law. So you're tracking F, M, and A, forces, mass, and acceleration. And you just want to keep track of adding up all the forces that are acting on the object. Because forces are vectors, the positives and negatives indicate the direction in which the forces are acting. So I don't call it a subtraction, I call it a vector addition, and I let the positive or negative be brought on by that vector specifically. So let's dive in right now. I have a 1,500 kilogram car traveling to the right. I'm going to assume it means horizontally. It encounters 550 newtons of friction. If the force produced by the engine is 2,000 newtons, determine the car's acceleration. So this is what I consider a first level problem or a forward problem, because what you're solving for, the equation's already set up for it, so there's no manipulation at all. So what I stress really, really heavily is the drawing, the DEPS, the diagram is really important here. And if I stay with the conventional way I've used so far is, I'm just going to use a dot for the car. Again, I'm not being very imaginative here. And I'm just going to write M is 1,500. I'll write a little larger next time. The acceleration we don't know. And I'm only going to be looking at the forces acting in the horizontal direction. So if I have the car moving to the right, friction is one of those forces that you can only determine the direction in which the force is applied once you see the way the object is moving. So if it's moving to the right, friction is always an oppositional force. So that means that the friction vector is going to be opposing or acting as a leftward acting force. So FF equals 550, and typically, because I'm really particular on this, I want to make sure I know numerically I'm going to be using a negative on that when I do the Newton's law calculation. And then we go back to, there's an engine force, and the engine force is going to drive it in the direction of motion because that's what engines do. So FE is, for me, is just force of the engine. That's going to be 2,000 newtons. And just to be specific here. So that is what I consider a completely labeled free body diagram right there. So that's a lot of what you're doing here. Now because we're looking at solving for the acceleration rate, it's going to be really easy. Because we know that the acceleration rate is the net force divided by the mass. Now the net, again, I'm going to be very specific about this. This is the sum of the two forces acting. So the frictional force and the engine force. There's no reason for the way I wrote them. It's just that was the first force encountered in the problem, so I wrote it first. And now we just kind of put the numbers in here. Friction is a negative 550. We're going to add that to a 2,000 Newton force to the right. And all that force has to move an inertia equivalent to 1,500 kilograms. So I'm going to do some quick number punching here. So I get 1,450 newtons of force is acting on 1,500 kg of mass. I use a 2 decimal rule, so 0.97 meters per second squared is the acceleration rate. So that's how you do what I call a forward solving problem, where you know this stuff and you just have to work the numbers to get that. I'd like to look at one where you're not just solving for acceleration. Let's look at one where you're going to solve for a force. So now we have an example of a problem where they give you the acceleration and they're asking for friction, which means you're going to be solving for a force. So there's Newton's second law. It might have magically appeared there. We'll check. And I'm going to start out again with my free body diagram. Free body diagram or force diagram. So again, we'll stay with the boring convention of having the dot represent the sofa. Let's see, this is a 150 kg sofa, and I know the acceleration. I'm just going to say positive 2 meters per second squared because to the right for me is positive. And I added a direction in here just to make things easy for everybody. You can pick your direction as long as you have friction opposing the other way. This is just the way I chose to do this. So they start by giving me now combined force. Don't get caught up on this. Combined force means both of these people are producing that in total. That's what the combined is going to mean. It may seem self-explanatory, but if I don't say it, sometimes that opens things up. So I'm just going to say F push equals 4,000. And if it's moving, unless otherwise stated, you can assume that friction is not present in these problems. So if I'm asking for a frictional force, if they're pushing to the right and this thing is accelerating to the right, then my FF is back here. Force of friction equals question mark. And so we're solving a little differently. This requires a little more algebra. So if we set this up, I'm going to expand this out a little more and say, well, the net force is made up of the push and the frictional force. Again, noting I'm using plus because I'm going to add these vectors together and let the directionality be carried by the vector themselves. Don't assume it's a negative yet. Let the math tell you it's a negative. And we'll divide that by the mass. So now we'll put numbers in here. Plus 2 meters per second squared equals, now we know the push force, 4,000 newtons, plus some other force we don't know, and then the mass is 150 kilograms. Now, two schools of thought on this. This equation, if you're always ending up with an unknown force, this can be done via cross multiplication. So 300 on this side, then 4,000 plus FF. If you want to follow the algebraic rules of, well, I got to isolate that, but it's divided by the 150, so I'm going to multiply 150 kg both sides. A kilogram times a meter per second squared is a newton. So now we're going to go back to, we have 300 newtons is what remains after the pushing and the pulling. This equals 4,000 on this side, plus the force of friction. So it looks okay. So if you just start to work the numbers here, subtract 400 from both sides, you're going to see that this comes out to be, I'll stay with that color. So it's a massive force of friction here. If they're pushing with 400, this is basically saying you have 300 left over after the push and the friction, because the mass times the overall acceleration rate is what the result is. So the frictional force is 3,700. And note that it is showing you it is opposing. So don't put that minus sign in. So that is how you would solve for an unknown force. That should take care of most of the examples. The only other one to keep in mind is the possible third permutation is if they give you the forces and the acceleration and they don't give you the mass. You do it the same way, you just work what you know, do some algebraic manipulation to get the mass by itself. In that case, remember, if mass is on the bottom, depends on how many steps you want to do, multiply by mass, and then divide by acceleration. All right, or if you're really good and are familiar with algebra, you can do the flip rule. M goes up here, A goes down here, you've just done 2 steps in one. That's it for today, guys. Just a couple of horizontal multis. And have a good day. Bye-bye.